What is time? Take a moment and think about something we experience every second of our lives. Time, it moves forward. It never stops. It seems constant and unavoidable. We measure it with clocks, organize our lives around it, and feel its passage in every memory we create. Days turn into years, moments turn into history, and the universe itself appears to unfold through time. For most of human history, time was treated as something simple and universal, a steady flow moving from the past to the future. But modern physics has revealed something extraordinary. Time may not be what we think it is. For centuries, the dominant scientific view of time came from Isaac Newton. In Newton's universe, time was absolute. It flowed at the same rate everywhere, for everyone, regardless of motion or location. Whether you were standing on Earth or traveling through space, time moved forward in exactly the same way. This idea seemed obvious because it matched our everyday experience. Clocks ticked steadily, planets moved predictably, and the universe appeared to operate like a perfectly synchronized machine. Then, at the beginning of the 20th century, Albert Einstein changed everything. Einstein's theory of relativity showed that time is not universal at all. Instead, time is deeply connected to space, forming a four-dimensional structure known as space-time. In this framework, time can stretch, slow down, and even behave differently depending on motion and gravity. One of the most surprising consequences of relativity is something called time dilation. If you travel at extremely high speeds, close to the speed of light, time for you will move more slowly compared to someone who remains stationary. Astronauts aboard spacecraft moving at high velocities actually age slightly more slowly than people on Earth. Gravity also affects time. The stronger the gravitational field around you, the slower time passes. Near massive objects such as neutron stars or black holes, time slows dramatically. To an outside observer, clocks near a black hole appear to tick more slowly and more slowly as they approach the event horizon. This is not just theoretical speculation. Modern GPS satellites must account for both gravitational time dilation and motion-related time dilation in order to provide accurate positioning on Earth. Without these corrections, GPS systems would accumulate errors of several kilometers per day. Relativity, therefore, reveals something astonishing. Time is not a fixed background for the universe. It is flexible, dynamic, and deeply connected to the structure of space. Yet relativity is only part of the story. When physicists explore the microscopic world through quantum mechanics, time becomes even more mysterious. In quantum theory, particles do not behave like classical objects, moving along well-defined paths. Instead, They exist as wave-like probability distributions that evolve over time according to mathematical equations. But here, a new question arises. What exactly is time in these equations? In many of the deepest equations of theoretical physics, time appears only as a parameter, something assumed rather than explained. In fact, when physicists attempt to combine quantum mechanics with general relativity to create a theory of quantum gravity, something strange happens. Time disappears from the equations entirely. One famous example is the Wheeler-DeWitt equation, sometimes described as the wave function of the universe. This equation attempts to describe the entire universe as a quantum system. But unlike most equations in physics, it contains no explicit time variable. In this framework, the universe does not evolve through time in the traditional sense. Instead, time may emerge from relationships between different parts of the system. This idea suggests that time might not be fundamental at all. It may be an emergent phenomenon. Just as temperature emerges from the motion of molecules in a gas, time might emerge from deeper processes occurring within the structure of reality. Another profound mystery related to time is known as the arrow of time. In our everyday experience, time seems to move in only one direction, from the past toward the future. We remember the past, but we do not remember the future. Broken objects do not spontaneously reassemble themselves. Heat flows from hot objects to cold ones, not the other way around. But the fundamental laws of physics do not strongly prefer a direction of time. Many physical equations work just as well forward as backward. So why does time appear to move in only one direction? The most widely accepted explanation involves entropy, a concept from thermodynamics. Entropy measures the level of disorder in a system. According to the second law of thermodynamics, entropy tends to increase over time. The universe moves from more ordered states to more disordered states. This increase in entropy may give rise to the arrow of time. In other words, the flow of time we experience may be closely tied to the gradual increase of disorder throughout the universe. But even this explanation raises deeper questions. Why did the universe begin in such a low entropy state? Why did time have a direction from the beginning? These questions remain some of the most profound mysteries in cosmology. When we look at the universe on the largest scales, time becomes even more intriguing. The entire cosmos has a history stretching back nearly 14 billion years. From the Big Bang to the formation of galaxies, stars, and planets, cosmic time provides a framework for understanding the evolution of the universe. Yet even the Big Bang may not represent the true beginning of time. Some theories suggest that time itself may have started at that moment. Others propose that time could extend beyond the Big Bang through cycles of cosmic expansion and contraction. Still others suggest that our universe may be one of many universes in a larger multiverse where time behaves differently in different regions. At present, science does not have a final answer, and perhaps that is what makes the study of time so fascinating. Time governs every process we observe in the universe. It shapes the evolution of stars, the motion of galaxies, and the development of life itself. Yet the deeper scientists investigate its nature, the more elusive it becomes. What seems obvious in everyday life becomes mysterious when examined through the lens of modern physics. Time may slow down. It may emerge from deeper structures. It may even behave differently in different parts of the cosmos. The universe continues to challenge our assumptions about what time really is. And as scientists explore the boundaries of knowledge, new theories and experiments may one day reveal answers that transform our understanding once again. Until then, time remains one of the greatest mysteries in physics. A concept so familiar, yet so profoundly complex. Time, however, becomes even more mysterious when physicists begin to ask a deeper question. Is time something that truly exists in the fundamental structure of the universe? Or is it simply a feature that emerges from the way we experience reality? At first glance, the answer seems obvious. Everything changes. Events occur one after another. Stars are born, burn for billions of years, and eventually collapse. Galaxies collide and reshape themselves over cosmic time. From the perspective of human experience, time appears to be one of the most basic ingredients of reality. Yet when scientists attempt to describe the universe using the deepest equations of physics, time often behaves in ways that challenge our intuition. In some theoretical models, time does not appear as a fundamental variable at all. Instead, it emerges from relationships between different physical systems, suggesting that what we perceive as the flow of time may be a consequence of deeper processes occurring within the structure of the universe. To understand this idea, imagine a universe described entirely by relationships rather than by an external clock. In such a universe, physical systems would change relative to each other. But there would be no universal ticking clock measuring the passage of time. Instead, time would arise from the comparison between different states of the system. Some physicists believe that this relational view of time may provide clues to one of the greatest unsolved problems in science: how to unify quantum mechanics and general relativity. Both theories describe reality with extraordinary precision, yet they treat time in fundamentally different ways. In relativity, time is woven into the fabric of space-time and influenced by gravity. In quantum mechanics, Time often appears as a background parameter against which events unfold. Reconciling these two views remains one of the central challenges in theoretical physics. Another fascinating aspect of time emerges when we consider the possibility of traveling through it. Science fiction often explores the idea of time machines, but modern physics has shown that certain forms of time travel are not entirely impossible in principle. Einstein's equations allow solutions in which space-time curves in such a way that paths through time loop back on themselves. These hypothetical structures, known as closed time-like curves, would theoretically allow an object to return to its own past. However, the conditions required to create such structures appear to be extremely extreme, involving forms of matter or energy that may not exist in nature. Even if time travel to the past were theoretically possible, it would raise paradoxes that challenge our understanding of causality. One famous example is the grandfather paradox. Imagine traveling back in time and preventing your own grandfather from meeting your grandmother. If that happened, your parent would never be born, and therefore you would never exist. But if you never existed, you could not travel back in time to prevent the meeting in the first place. Paradoxes like this suggest that the universe may contain mechanisms that prevent contradictions from occurring. Some physicists propose that the laws of nature might enforce consistency, meaning events in the past cannot be changed in ways that would create logical contradictions. Others believe that time travel might instead create alternate timelines or parallel universes where different histories unfold. Even without time travel, the concept of time becomes increasingly complex when we examine the universe on cosmological scales. The entire history of the universe, from the Big Bang to the present day, can be seen as a vast timeline stretching across billions of years. In the earliest moments after the Big Bang, the universe was an incredibly hot and dense environment where particles and radiation interacted in ways that are still being studied today. As the universe expanded and cooled, atoms formed, stars ignited, and galaxies gradually assembled into the large-scale structures we observe today. Over cosmic time, gravity has sculpted the universe into a network of galaxy clusters, filaments, and enormous cosmic voids. Yet even this cosmic timeline raises questions about the true nature of time itself. Some theories suggest that time may have begun at the moment of the Big Bang. In this view, asking what happened before the Big Bang might be meaningless, because time itself did not exist before that event. Other theories propose that our universe may have emerged from a previous cosmic phase, perhaps through a bounce or a cycle of expansion and contraction. In such models, time might extend infinitely into the past, with universes forming and dissolving repeatedly across an endless cosmic history. The deeper physicists investigate time, the more they realize that it may not behave as a simple, linear flow from past to future. Instead, time may be intertwined with the fundamental structure of reality in ways that we are only beginning to understand. Some approaches to quantum gravity suggest that the universe may be better described in terms of information rather than space and time. In these models, the geometry of space-time itself could emerge from patterns of quantum entanglement between microscopic degrees of freedom. If this idea proves correct, then time may ultimately arise from the way information is processed and distributed throughout the universe. These possibilities illustrate a remarkable truth about science. The concepts that seem most familiar can sometimes turn out to be the most mysterious. Time is something we experience constantly, yet its true nature remains one of the deepest puzzles in physics. Every clock we build measures time, but none of them explain what time actually is. As our understanding of the universe continues to evolve, future discoveries may reveal that time is not a fundamental dimension of reality, but rather a feature that emerges from deeper physical laws. And if that is the case, then the universe may be even stranger than we currently imagine. Still, within